do question 3, part 3. They ask, what are the slopes dt dx for the direct wave and the head wave on a tx plot in tx space? So they're asking for slopes for both a direct wave and a head wave. Let's do the direct wave first. It's by far the simplest of the cases. I've gone ahead and taken the liberty of drawing a simplified diagram here of a plausible earthquake scenario. This little line here represents a fault. Let's say it's a reverse fault. Why not? Because of the fault symbols there. You have a fault. There's a point at which an earthquake is generated in the subsurface. The velocity of that subsurface material is v1. And we have a recording station here, up on the surface, with all you happy folks studying geophysics. And you want to know what the slope of this earthquake is going to look like, what the slope of the direct arrival wave is going to look like on TX plot. Well, what is the direct arrival? The direct arrival, the direct wave, is going to be the ray path that travels the shortest distance between where the earthquake occurs and where you record it. In this case, the straight line between this point here and your recording station. That is the direct wave. That is the direct ray path. And we need to calculate the slope dx dt for that wave path. So when you do slopes in other math courses, you usually have it, rise over run, y over x, changing y over changing x. In this case, we're doing it in TX space. We're asking for what is the change in time over the change in distance for this direct arrival, for this direct wave. I'm sorry, I keep saying direct arrival. Same thing. For this direct wave, what is the change in time per change in distance x? And to do that, first we need to know what the distance, or what the time and distances are. So for this direct wave, we're going to assume that this path right here has a certain length x. We're going to call that x. That's the distance that the direct wave travels. And how much time does it take to get there? Well, time is simply a measure of what? It's a measure of distance over velocity, right? If I want to know how long it's going to take me to get from here to the University of Houston, well, now it's going to be quite a ways. It's 1,700 miles. But if we want to know how long it's going to take us to get from where we are to U of H, first we need to know the distance from where we are to the University of Houston, and we need to know about how fast we'll be going. So if we're driving, we'll say, oh, it's 5 miles away, and we're going 30 miles per hour. So 5 miles divided by 30 miles per hour, we can solve for the amount of time that it takes to get there. Same thing for earthquakes. If we know the distance, x, in this case it's x, and we know the velocity that that wave will be traveling, v1 in this case, we can solve for time, right? T equals x divided by v1. Very easy, very simple, right? And in order to get dt dx, we simply have to take the first derivative of that, right? So what is the first derivative of t equals x over v1? The first derivative is dt over dx is equal to 1 divided by v1. You probably all know how to take first derivatives, so that's pretty easy. There is the answer to the first half of question 3, part 3. So next we're going to do a little bit more drawn out version of this dx dt for the head wave. It's going to be a little bit more complicated, so we'll do it in the next video.